In this lecture, I am going to present what is conjugate beam, what are the different end supports in original beam and the corresponding section of conjugate beams, and how to determine the slope and deflections of various beams using conjugate beam methods. Then I would like to solve some problems using this method. First, we have to know what is slope and deflection. When a beam is subjected to transverse loading, it bends and moves downward direction. This downward movement of the beam from its original position is called the deflection of the beam. And the angular rotation of the beam with respect to the original position is called the slope of the beam. Then coming to the conjugate beam, first we have to know what is conjugate beam. The conjugate beam can be defined as an imaginary beam of same span as the original beam loaded with M/I diagram of the original beam, such that the shear force and bending moment at a section will represent the rotation and deflection at that section in the original beam. These are the different end supports in original and corresponding conjugate beams. If the end of the original beam is roller support, then you have to take in the conjugate beam also roller support. If the end of the original beam is hinge support, then you have to take in conjugate beam also hinge support. If the end of the original beam is fixed support, so in conjugate beam you have to take the fixed support as a free end. So here you see at roller support the rotation at the roller end is not equal to 0, but the deflection is equal to 0. But in conjugate beam at the same section, that is the shear force is not equal to 0 and the bending moment is equal to 0. Then here this is the hinge support. So at hinge support the slope not equal to 0 and the deflection is equal to 0. But in conjugate beam at the hinge support the shear force is not equal to 0 and bending moment is equal to 0. And if in the original beam, if the end is fixed support, so here the slope is 0 and the deflection is 0. But in conjugate beam, so at the free end the shear force is 0 and the bending moment is 0. So here in original beam, if the end is free end, you have to take in the conjugate beam fixed end. If in original beam, if there is present the interior support, so in conjugate beam you have to replace by internal hinge. And in the original beam, if there is present the interior hinge, so in the conjugate beam you have to replace by the interior support. So here if in the original beam, if the end is free end, so here the slope is not equal to 0 and the deflection is not equal to 0. But in the corresponding section of the conjugate beam, the end is fixed, so here the shear force is not equal to 0 and the bending moment is not equal to 0. And in this figure, in the interior support of the original beam, so here the slope is not equal to 0 and continuous and the deflection is equal to 0. But in corresponding section of the conjugate beam, so you have to take the interior hinge. So at the interior hinge, the shear force is not equal to 0 and the continuous and the bending moment is equal to 0. Similarly in this figure, in original beam, due to the internal hinge, so here the slope is not equal to 0 and discontinuous and the deflection is not equal to 0. But the corresponding section of the conjugate beam, so you have to take the interior support. So here the shear force is not equal to 0 and discontinuous, and M is also not equal to 0. So these are the different end supports in original beam and in conjugate beam. Then look at this figure. Here this is the relation between the original and corresponding conjugate beams. So this is the original beam and this is the conjugate beam. In this figure, if the original beam is simply supported beam, so you have to take the conjugate beam is also simply supported. If the original beam, if one end is hinge support and other end is roller support, and also in the conjugate beam also you have to take one end is hinge support and the other end is roller support. And if the original beam is fixed beam, so in the conjugate beam you have to take the fixed end as a free end and free end as a fixed end. And this is the beam. So here this support is hinge support and this is the interior support and this end is free end. So this is the original beam. So you have to take in the conjugate beam, the hinge support is also hinge support, and at the interior support you have to take the internal hinge, and at the free end you have to take the fixed support. So here this is the original overhanging beam. So here this two end is free and this is the interior support. So in the conjugate beam you have to take the free end as a fixed end and the interior support as a internal hinge. And this is the beam. Here this end is fixed and this is the internal hinge and this is the hinge support. This is the original beam. So in corresponding conjugate beam, so you have to take the fixed end is as a free end and the internal hinge as a interior support, and hinge support you have to take as a hinge support in the conjugate beam. And this is the beam. So here both ends are fixed and this two is the internal hinge. This is the original beam. So you have to take in the conjugate beam the fixed end as a free end and the internal hinge as a interior support. So this is the conjugate beam. And here this is the beam. So here this is hinge and this is internal hinge. This is hinge support, this is internal hinge, this is hinge support, this is internal hinge, and this is fixed support. So these two supports, hinge supports, interior support, and these three internal hinge. So in corresponding conjugate beam, you have to take the end hinge support as a hinge support and the internal hinge as a interior support and interior support as a internal hinge, and the fixed end you have to take as a free end in the conjugate beam. So this is the original beam and this is the conjugate beam. So when you want to find out the slope and deflection, so you have to take these are the different original and corresponding conjugate beams. So here you see at fixed end in the original beam, here the slope 0 and deflection 0. So you have to take in the conjugate beam, this is the free end. So at the free end here the shear force is 0 and bending moment is 0. At fixed end in the original beam, rotation and deflection are 0. Hence in the corresponding conjugate beam, shear force and bending moment should be 0. This end condition exists at the free end. So this is the fixed end and this is the free end. So at free end, so there is the shear force and bending moment is 0, and at the fixed end there is the slope and deflection is 0. Then coming to conjugate beam method. The conjugate beam method is also called as the method of elastic weight. This is similar to the moment area method. Geometrically, this is much easier to apply when considering simply supported beams. This method is very convenient to find the slope and deflections of various beams having varying flexural rigidities. So in this method, the shear force at any section of the conjugate beam is equal to the slope of the elastic curve at the corresponding section of the actual beam. Similarly, the bending moment at any section of the conjugate beam is equal to the deflection of the elastic curve at the corresponding section of the actual beam. In this method, first draw the shear force and bending moment diagram for the given beam. Then the moment diagram drawn is divided by the flexural rigidity to obtain the M/I diagram, and the same applied on the imaginary beam as a load. Then using this M/I diagram, the reaction of the imaginary beam are calculated. Then the shear force of the imaginary beam or the location where the slope of the original beam is required is determined from the M/I diagram. Similarly, the bending moment of the imaginary beam where the deflection in the original beam required is determined from the M/I diagram. These are the procedures you have to follow to find out the slope and deflection by conjugate beam methods. Then coming to the sign convention which is used in conjugate beam method. So in this method, the sagging moment is taken as positive and the hugging moment is taken as negative. This is the sagging moment, so you have to take the sagging moment as positive, and this is the hugging moment, and this you have to take as a negative. The left side upward force or the right side downward force is you have to take as a positive shear, and left side downward force and the right side upward force you have to take as a negative shear. Then the positive moment diagram of the actual beam is a downward load for the conjugate beam. Similarly, the negative moment diagram of the actual beam is a upward load for the conjugate beam. The positive shear of the conjugate beam corresponds clockwise slope of the actual beam and vice versa. Similarly, the positive bending moment of conjugate beam corresponds to downward deflection of the actual beam. So these are the sign conventions you have to follow for solving any beam by this method. Then coming to the first problem, a simply supported beam is subjected to a concentrated load at midspan. Calculate the end slopes and midspan deflection of the beam by conjugate beam method. EI is constant throughout the beam. So this is the simply supported beam, and here the load is present at the midpoint of the beam W, and the length of the beam is given L, and this is the hinge support and this is the roll-out support. So you have to find out what is the slope at A and slope at B, and you have to find out what is the deflection at C. Using this method, so first you have to draw the bending moment diagram of this simply supported beam. So this is the bending moment diagram. So because here the load is present at the midpoint of the beam, so this is the bending moment diagram. So the bending moment at the end A and B is 0, and the maximum bending moment is equal to WL/4. That is obtained at the midpoint of the simply supported beam, WL/4. This is the positive bending moment diagram. You have to take the M/I diagram as a loading of the conjugate beam. So this is the M/I diagram. This is the M/I diagram. So here this is WL/4, the bending moment, the maximum bending moment. So here you have to divide by EI. So this is the M/I diagram, and this M/I diagram is the loading for the conjugate beam. So this is the conjugate beam. So here this is the loading. So here you have to take the support A dash, B dash and C dash. You have to find out in the original beam, so at the end what is the slope, and you have to find out what is the midspan deflection in the original beam. So in this method, so you have to find out what is the shear force at the end of the beam, and where you want to find out the slope, and you have to find out what is the bending moment. So where you want to find out the deflection. The end slope of the real beam A is equal to the shear at A dash in conjugate beam. What is the slope you have to find out in the real beam at A? In conjugate beam you have to find out what is the shear force at the corresponding section. Similarly, you have to find out what is the slope in the original beam at B. In conjugate beam you have to find out what is the shear force at B dash at the corresponding section. Here the load is symmetrical, so first you have to find out what is the reaction at the both ends. The reaction at both ends, RA dash is equal to RB dash, that is equal to the total area of the load is equal to half into L WL by 4EI. So this is the total area of the load divided by 2. So this is the reaction at both ends, RA dash and RB dash. So RA dash and RB dash is equal to half into the total area of the M by I diagram. So total area of the M by I diagram is equal to half into L into WL by 4EI. So this is equal to WL square by 16EI. So the reaction at both ends, that is RA dash and RB dash, that is equal to WL square by 16EI. Then find out what is the shear at B dash. So shear at B dash, that is equal to minus RB dash is equal to minus WL square by 16EI. So here this is upward reaction. So the shear at B dash, that is equal to minus RB dash, and that is equal to minus WL square by 16EI. Similarly, the shear at A dash, so this is left side upward direction. The left side upward direction, the shear force that you have to take positive. So shear force at A dash, that is equal to RA dash, and that is equal to WL square by 16EI. Then you have to find out what is the end slope at A in the original beam. So that is equal to theta A is equal to RA dash, that is equal to WL square by 16EI. Similarly, the end slope at B is equal to theta B is equal to minus RB dash is equal to minus WL square by 16EI. So here you see, so the slope at A, theta A is equal to WL square by 16EI, and slope at B, theta B is equal to minus WL square by 16EI. At the slope at A is equal to WL square by 16EI positive, so here the clockwise rotation takes place, and at the slope at B is equal to minus WL square by 16EI, so here the anti-clockwise rotation takes place. So theta B, that is equal to WL square by 16EI anti-clockwise rotation, and theta A is equal to WL square by 16EI clockwise rotation. Then find out the deflection of the beam. The midspan deflection of the actual beam is equal to the bending moment of the conjugate beam at midspan. So here you have to find out the bending moment of the conjugate beam at midspan. So here you have to find out the bending moment. So you have to find out the bending moment MC dash. So that MC dash, that is equal to the deflection of the original beam at C. So here you have to take the moment either from the right side or from the left of the section. So RA dash into L by 2 minus, you have to take the area of this one, half into L by 2 into WL by 4EI, half into L into WL by 4EI into the centroidal distance. So this is equal to L by 2 into 1 by 3. L by 2 into 1 by 3. So MC dash is equal to RA dash into L by 2 minus half into L by 2 into WL by 4E into L by 6. Then after simplification, MC dash is equal to WLQ by 48 EI. So this is the midspan deflection of the actual beam. Delta C is equal to the bending moment at the corresponding section of the conjugate beam, that is equal to WLQ by 48 EI. So this is the midspan deflection of the original beam, and this is the end slopes of the original beam by conjugate beam method. Then coming to the second problem, a cantilever beam AB is subjected to a uniformly distributed load of W per unit length. Compute the slope and deflection at B by conjugate beam method. Take EI is constant throughout the beam. So this is the cantilever beam, and here the length of the beam is L. The end A is fixed and end B is free end, and the load is present W per unit length throughout the length. So in conjugate beam method, so here you have to find out what is the slope and deflection at the free end of the beam. What is the procedure? So first you have to draw the bending moment diagram of the cantilever beam. The bending moment at B is equal to 0 and bending moment at A is equal to minus WL square by 2, and this is the parabolic. The bending moment diagram is parabolic, and this is the negative bending moment diagram. Then you have to draw the M by I diagram, and that M by I diagram is loading for the conjugate beam. As the bending moment diagram is negative, you have to take the direction of the load, that is in upward direction. So this is the conjugate beam. So here you have to take the load in upward direction as the bending moment diagram is negative, and here this is the M by I diagram. So the bending moment WL square by 2, and you have to divide by EI. So this is the M by EI diagram. So here this is WL square by 2 EI, and here this is 0. As you know, if the original beam is cantilever, so at the fixed end, so you have to take in conjugate beam, that is free, and the free end you have to take in the conjugate beam, this is fixed. So this is the conjugate beam. So here the fixed end become the free, and the free end become the fixed in the conjugate beam. And this is the M by A diagram, and here the loading is upward direction as the bending moment is negative. So here you have to find out the slope and deflection at the end B of the original beam. So in conjugate beam you have to find out what is the shear force at B dash and what is the bending moment at B dash. So end slope at B of the real beam is equal to the shear at B dash in the conjugate beam. Similarly, the end deflection at B of the real beam is equal to the bending moment at B dash in the conjugate beam. So here you have to find out the shear force and bending moment. So first to find out what is the shear at B dash. So shear at B dash is equal to VB dash. So you have to find out shear at B dash. So that is equal to VB dash. So you have to take the what is the total area of the load. The bending moment diagram is parabolic. So here that area is equal to 1/3 into L into WL square by 2EI. So the shear at B dash is equal to VB dash is equal to 1/3 into L into WL square by 2EI. So this is equal to WLQ by 6EI. So this is the shear at B dash. So as you know, so in the original beam you have to find out what is the slope at B, that is equal to theta B. So is equal to the shear at B dash in the conjugate beam is equal to WLQ by 6EI. So this is the slope at B. Similarly, you have to find out what is the bending moment at B dash in the conjugate beam. So that is equal to the deflection at B in the original beam. So you have to find out what is the moment of this area about the B dash. So the area of this one is 1/3 into L into WL square by 2EI, and the moment about this end is equal to 3/4 into L. This is the centroidal distance, and the bending moment at B dash is equal to MB dash is equal to 1/3 into L into WL square by 2EI, and the centroidal distance that is equal to 3/4 into L. So this is equal to WL fourth by 8EI. So this is the bending moment at B dash. So this is equal to the deflection at B of the original beam. The deflection at B, that is equal to delta B is equal to MB dash is equal to WL fourth by 8EI. Then coming to the third problem, a simply supported beam is subjected to a uniformly distributed load of W per unit length. calculate the end slopes and midspan deflection of the beam by conjugate beam method, where EI is constant throughout the beam. So here this is the simply supported beam and the length of the beam is L, and here having the load W per unit length throughout the span. So here you have to find out what is the slope at A and what is the slope at B and what is the deflection at C, midspan deflection. As you know from the procedure, so first you have to draw the bending moment diagram. Here the bending moment diagram is parabolic and the maximum moment you get at the midsection of the simply supported beam. So the maximum bending moment, that is equal to WL square by 8 at the midsection. But at the end A and B, the bending moment is equal to 0, and this is parabolic diagram. So this is the bending moment diagram of the simply supported beam. Next step, you have to draw the M by I diagram, and that is loading for the conjugate beam. So this is the M by I diagram, and this is the loading for the conjugate beam. So this is the conjugate beam, and here you have to take the M by I diagram as a loading of the conjugate beam. So this is the M by I diagram. So here the bending moment is equal to WL square by 8. So you have to divide it by EI. So this is the M by I diagram, WL square by 8 EI. And here the M by I diagram 0, and here also 0. So this is A dash, B dash and C dash. And this is the conjugate beam. If the original beam is simply supported end, so in the conjugate beam also you have to take this is simply supported end. You have to find out what is the slope at A and B of the original beam. In conjugate beam, you have to find out what is the shear force at A dash and what is the shear force at B dash. Here the end slope of the real beam A is equal to the shear at A dash in conjugate beam. Similarly, the end slope of the real beam B is equal to shear at B dash in conjugate beam. You have to find out what is the slope at A and B of the real beam. So that is equal to the shear force at A dash and B dash in the conjugate beam. So first you find out what is the reaction at both ends, RA dash and RB dash. So here the loading is symmetrical. The half of the load will be shared by each reaction component. The half of the load will be shared by each reaction component. So first you find out what is the total area of this M by I diagram, and this area divided by 2 is equal to RA dash is equal to RB dash. So the reaction at both ends is equal to RA dash is equal to RB dash, that is equal to half, and what is the total area of this M by I diagram. So the total area, this is equal to 2/3 into base into height, 2/3 into L into WL square by 8 EI. So this is the total area of this M by I diagram divided by 2. This is equal to the RA dash and RB dash. RA dash and RB dash is equal to WLQ by 24 EI. Then find out what is the shear at B dash. Here the reaction is in upward direction. So the shear at B dash is equal to minus RB dash is equal to minus WLQ by 24 EI. Similarly, find out what is the shear at A dash. So here this is upward direction, but this is left side. The left side upward force is you have to take as a positive, and right side upward force you have to take as a negative. So the left side upward force, the shear force at A dash is equal to RA dash is equal to WLQ by 24 EI. Then after knowing the shear force at B dash and A dash, then you can find out what is the end slope at A and the end slope at B. The end slope at A is equal to theta is equal to RA dash is equal to WLQ by 24 EI. Similarly, the end slope at B is equal to theta B is equal to minus RB dash is equal to minus WLQ by 24 EI. As you know, here you got theta is equal to WLQ by 24 EI, positive value. So the rotation takes place in clockwise direction, and here theta B is equal to minus WLQ by 24 EI. So here the rotation takes place in anti-clockwise direction. So theta is equal to WLQ by 24 EI clockwise rotation, and theta B is equal to WLQ by 24 EI anti-clockwise rotation. Then find out the deflection of the simply supported beam at the mid section. The mid span deflection of the actual beam is equal to the bending moment of the conjugate beam at mid span. You have to find out what is the mid span deflection of the actual beam. That is equal to the bending moment at the corresponding section of the conjugate beam. So the bending moment of the conjugate beam at mid span is equal to MC dash, and that you have to find out. So here you have to find out the bending moment at the C dash. Either you have to take the right side of this section or left side of section. You have to take what is the moment here. So the MC dash is equal to RA dash into L by 2 minus what is the area of this half portion. This is equal to 2/3 into L by 2 into WL square by 80I. 2/3 into L by 2 into WL square by 80I. This is the half of this area, and take the centroidal distance. This is RA dash into L by 2 minus 2/3 into L by 2 into WL square by 80I into the centroidal distance. This is equal to 3 by 8 into L by 2. The centroidal distance of this parabola, this one. So from the centroid to this section, so you have to take, this is the length L by 2, and here you have to take 3 by 8 into L by 2. This is the centroidal distance of this area. Then MC dash is equal to RA dash into L by 2 minus 2/3 into L by 2 into WL square by 80I into 3 by 8 into L by 2. Then after simplification, the MC dash is equal to WLQ by 24 EI into L by 2 minus WL fourth by 128 EI. Then MC dash is equal to 5 by 384 WL fourth by EI. So this is the bending moment at mid span of the conjugate beam. So this is equal to the deflection at the mid span of the original beam. The mid span deflection of actual beam is equal to delta C is equal to MC dash is equal to 5 WL fourth by 384 EI. So this is the mid span deflection of the actual beam. Then coming to the fourth problem, a simply supported beam of length L carries a central point load W. If the moment of inertia is 3I at the left half and I at the right half, then find the slope or the supports and deflection at the mid span. So here this is the beam. So here the moment of inertia for left side is given 3I and right side is given I, and this is A, B, C, and the length of the beam is given L. So here you have to find out what is the slope at A and what is the slope at B, and you have to find out what is the mid span deflection at C. So this is the reaction at A. The reaction is W by 2, and at B the reaction is W by 2, because the load is present at the midpoint. So the reaction at A and the reaction at B both are equal, that is equal to W by 2. So first you draw the bending moment diagram, as you know from the procedure. So first you have to draw the bending moment diagram of this beam. So this is the bending moment diagram of this beam, and here the maximum bending moment that is occurs at the midpoint. So that is equal to WL by 4, and this is the positive bending moment diagram. Then the next step, you have to draw the M by I diagram, and that M by I diagram is the loading for the conjugate beam. So this side the moment of inertia is given I, and this side the moment of inertia is given 3I. Here the bending moment is WL by 4. So for this side you have to take WL by 4EI, and for this side you have to take WL by 4 into 3I, 4 into 3EI, that is 12 into EI. WL by 12 into EI, you have to take this side, the M by EI diagram, and this side you have to take WL by 4EI. So this side, this height is equal to WL by 12 EI, and this height is equal to WL by 4EI. So this is the M by I diagram of the conjugate beam, and you have to take this M by I diagram as a load of the conjugate beam. So this is the end support A dash and this is B dash, and here the reaction at A dash is equal to RA dash and the reaction at B dash is equal to RB dash, and this is the C dash. So here you have to find out what is the end slope at A and B of the real beam. So that is equal to the shear at A dash and B dash in the conjugate beam. End slope of the real beam A is equal to the shear at A dash in the conjugate beam. Similarly, the end slope of the real beam B is equal to the shear at B dash in the conjugate beam. So here you have to find out what is the shear force at A dash and what is the shear force at B dash in the conjugate beam. So that is equal to the slope at A and slope at B of the real beam. So first you find out what is the reaction at A dash and B dash, that is RA dash and RB dash, by considering this is the load. Reaction in conjugate beam. Let RA dash and RB dash be the reaction in conjugate beam at A dash and B dash respectively. So taking moment about B dash, so RA dash into L, this is clockwise rotation, and due to this load this is anti-clockwise rotation. So you have to take the clockwise moment is equal to the anti-clockwise moment. RA dash into L is equal to, then first you take what is the moment of this area and take what is the moment of this area. So the moment of this area, so this area is equal to half into L by 2 into WL by 12 EI, and what is this centroidal distance? So this is equal to 1/3 into L by 2, 1/3 into L by 2 plus L by 2. Then take the moment of this area. So the moment of this area, so here half into L by 2 into WL by 4EI, and what is the centroidal distance about this point? So this is equal to 2/3 into L by 2. So here the taking moment about B dash, RA dash into L is equal to half into L by 2 into WL by 12 EI is equal to L by 2 plus 1/3 into L by 2 plus half into L by 2 into WL by 4 EI into 2/3 into L by 2. Then after simplification, RA dash is equal to 5 WL square by 144 EI. Then find out the reaction at B dash, RB dash. So by equating the upward force is equal to downward force. The upward force is equal to RA dash plus RB dash, and the downward force is equal to the area of this loading. So here area of this load is equal to half into L by 2 into WL by 12 EI, and area of this load is equal to half into L by 2 into WL by 4 EI is equal to RA dash plus RB dash. So RA dash plus RB dash is equal to half into L by 2 into WL by 12 EI plus half into L by 2 into WL by 4 EI. Then after simplification, RB dash is equal to 7 WL square by 144 EI. So this is the reaction at A dash and B dash in conjugate beam. Then find out the slope. The shear at B dash, first you find out what is the shear at B dash and what is the shear at A dash. The shear at B dash, that is equal to minus RB dash, as the reaction at B dash is in upward direction. So the right side upward force you have to take negative, and the left side upward force you have to take positive. So here this is upward, so shear force at B dash is equal to minus RB dash. Minus RB dash is equal to minus 7 WL square by 144 EI. Similarly, shear at A dash is equal to RA dash. So this is left side upward force you have to take positive, is equal to 5 WL square by 144 EI. Then find out what is the end slope at A of the real beam and end slope at B of the real beam. So the end slope at A is equal to theta A. So this is equal to the reaction at A dash in the conjugate beam is equal to 5 WL square by 144 EI. Similarly, the end slope at B is equal to theta B of the real beam is equal to the shear at B dash in the conjugate beam minus RB dash is equal to minus 7 WL square by 144 EI. So here you see as theta is equal to 5 WL square by 144 EI, positive value. So here the rotation takes place in clockwise direction, and here the theta b is equal to minus 7 WL square by 144 EI. Here the theta b is equal to minus 7 WL square by 144 EI due to negative. So here the rotation takes place in the anti-clockwise direction. So theta b is equal to 7 WL square by 144 EI anti-clockwise rotation. Then find out what is the midspan deflection of the actual beam. The midspan deflection of the actual beam is equal to the bending moment at the corresponding section in the conjugate beam. So here the bending moment of the conjugate beam at midspan is equal to MC dash. So you have to find out what is the bending moment at the midspan of the conjugate beam. Here you have to find out what is the bending moment. Either you have to consider the right side of the section or left side of the section, and you have to find out what is the bending moment at C dash. The MC dash is equal to RA dash into L by 2 minus area of this diagram half into L by 2 into WL by 12 EI and the centroidal distance. The centroidal distance, this is equal to 1 by 3 into L by 2. So the MC dash is equal to RA dash into L by 2 minus half into L by 2 into WL by 12 EI into 1/3 into L by 2. Then after simplification, MC dash is equal to WLQ by 72 EI. So this is the midspan deflection of the actual beam. Delta C is equal to MC dash is equal to WLQ by 72 EI. So this is the midspan deflection. Now all are clear what is conjugate beam, then how you have to find out the slope and deflection using the conjugate beam method.